It's not very what's actually that's why. But yourself, like that, I mean, but bro, you're stuck in a matrix. It's like you know, I'll try your ink. It's not oh, 45. What's this stuff? You know, why don't you do this? Plus your minus long.
Okay, page 26. Okay, we're talking about intermediate value theorem and squeeze theorem. These are both these are both theorems that I think are fairly intuitive. It's going to make sense to us without even having told. Like it's not going to feel like anything that we can't get to just by reasoning. So IVT intermediate value theorem for continuous function says that if the function is continuous on the interval from a to b, and let's say that these are my endpoints, right? So I know that one endpoint is either less than the other endpoint or vice versa, right? So either I'm starting off with a higher y value, ending with a lower y value, or I'm starting with a lower value and ending with a higher y value. Okay, so it doesn't really matter which one is higher, which one is lower. Now let's say that we wanted to find a y value that sits between a and b. And so according to IVT, there is a value c such that f of c is equal to that targeted limit as long as c values between a and b. So here's an example that I can say. Let's say I wanted to find a y value of 4. Okay, and I know that one endpoint has a y value of 10, and the other endpoint has a y value of 1. So can I guarantee that as long as the graph is continuous, that my graph is going to hit a y value of 4 somewhere between a and b? Yes, right. There's maybe it's more than 1, but as long as my graph is continuous and I'm starting at a value above my target, and if I'm ending below my target, I'm going to have to hit my target somewhere between. Okay. Likewise, if I'm starting at a value below my target and trying to hit, and then ending up with a value above my target, I'm going to have to hit my target somewhere between. So it makes sense without having to be told that this theorem exists. But later on, when we're trying to prove that a certain value exists, we can reference IVT to justify some of our answers. The only thing with IVT is that it's a little bit wordy in terms of the justification. No, there's multiple ways of doing it, of writing it out, but I'll show you the way that I feel is the most efficient. But there's multiple ways for you to represent that that this value exists. Okay, so below is a table of values for a continuous function f. So that tells us that we see the y values decreasing, increasing. It doesn't mean that it's only increasing, decreasing according to these values, but we do know that there's no surprise asymptote or holes in between. The graph is going to have to be continuous throughout the entire graph. So on the interval from 0 to 9, what is the minimum number of zeros? So basically, how many x-intercepts, what's the minimum number of x-intercepts that we can guarantee? 3, right? From 1 to -5, it's got to hit 0 at least once. From -5 to 3, it's got to hit a 0 at least once. And then from 7 to -1, it's got to hit 0 at least once. It doesn't mean that there could be more zeros, but based off of the data that we have, that's the minimum that we can say. And that's basically applying intermediate value theorem. We know that our function is continuous. We have, anytime we see a y value below turning to a y value above our target, we know that our target is going to be reached. We start off with a value above our target. We end up with a value below our target. We know our target is going to have to be reached somewhere between there as well. And likewise from 7 to -1. Okay. On the interval from 4 to 9, what is the fewest possible times that f of x equals to 1? Okay, so from 4 to 9, we're going from 3 to 7 to -1. Yeah, from 3 to 7, we can't guarantee that it's going to hit y value of 1, because it's possible for us to draw the graph from 3 to 7 without ever touching a y value 1. But from 7 to -1, we gotta cross y equals 1 at least one time. So yeah, exactly that. Okay, on the interval from 0 to 4, x value between 0 and 4, must there be a value of x for which f of x is equal to 2? Yes, right. And so it says to explain. Okay, so here's how we can, here's one way that we can represent intermediate value theorem in kind of like the fewest, in the kind of least wordy way possible. So first off, we're going to establish that f of 0 is equal to 1, f of 4 is equal to 3. So we have a y value below our target. We end up with a y value above our target. We know we got to reach our target at least once. So we can say this by IVT. Since our function is continuous, okay, and we want to specify the interval, even if the function is continuous for all real numbers, we are just concerned about our interval. So we're going to specify our interval. Okay. There is a value c such that f of c is equal to 2, since we have one endpoint showing a y value of 1, and 1 is less than 2, and 2 is less than 3 coming from the other endpoint. Now, there are other ways that you can write this out, but this is, I think, the most efficient way of getting full credit on AP exam. We want to be able to establish our condition that our function is continuous on closed interval. And we want to specify that we know that we can reach our target because our target is between our endpoints. And then we want to specify that our y value is one y value is below and one y value is above, and then also representing that our y values are coming from our endpoints. So if you say this in a different way, that's fine, but this is the way that we can write it out in the most, in the briefest way possible, basically. Okay, number 4, on the interval from 4 to 8, could there be a value of x for where f of x equals to -2? Yes, but there's no guarantee that our y value is equal to -2, right? And because our function is continuous, we know that it would definitely reach -2.
But since f of 4 and f of 8 are both above y equals -2, we can't guarantee it. But yes, there could be. Yeah, this one is more specifying that no, it's possible, maybe on a multiple choice question, but if that word got changed to, must there be a value, then we can say that there is no guarantee. Okay, let's try number 5. So read number 5 and see if we can apply right 5 or justify 5 like how we did number 3.
Okay, so we're looking at polynomial. Polynomial is continuous everywhere, but we just want to specify the continuity that we care about is between -1 and 5. And we want to establish where our endpoints are. Our endpoints is one endpoint has a y value of 3, the other endpoint has a y value of 21. And we know that 8 is safely between 3 and 21. So say by IVT, there's a value C such that f of C is equal to 8. We can guarantee a y value of 8 somewhere on the interval from -1 to 5, since one endpoint, f of -1, has a y value lower than 8. The other endpoint, f of 5, has a y value greater. Just make sure that you're comparing apples to apples. I've seen students in the past where they say, oh, 8 is not between -1 and 5, and therefore IVT doesn't apply. So make sure that you're understanding that, this interval is the x value. You still have to find the y values. We don't want to compare the 8 with the x values. We want to compare the 8 with the y values at these endpoints. Okay, let's just practice 16 and 17, and we can move on to squeeze theorem after that. And then we can practice writing out the reasoning so we can get comfortable with it. It's not hard, you just have to kind of practice writing it in a way that will earn full credit.
The students at interval with that one method. 2, 1.
-2 to 1. Yeah. Just so happens that the y value looks like the x values. Okay, but we want to compare with the y values. Okay, 17, g of x equals 1 over x. There's a potential issue for 1 over x, right? Because we know that 1 over x is not continuous everywhere. But between 2 and 5, we're safe, right? There is a vertical asymptote at x equals 0, but 0 is safely outside, or interval 2 to 5 is outside of our 1 restriction. So our function is continuous on the vector interval 2 to 5. The issue is that my y value is 1/2 and 1/5 is not favorable for applying intermediate value theorem, right? Because I can draw a graph from 1/2 to 1/5 without ever crossing -1. So the graph could hit y equals -1, but based off of the limited information that we can use to justify IVT, we can't guarantee it. Okay, any questions? Intermediate value theorem? Okay, next page. This is squeeze theorem or sandwich theorem. Okay, page 27. I just want you guys to start off with the top and the bottom one here. So let's just draw these two to begin with. Let's just do h of x and g of x. Let's start with these two to begin with. Okay, so let's say we have 3 functions, okay, and there is a established relationship between these 3 functions that says that g of x is going to be guaranteed to be less than or equal to every y value on f of x, and f of x is guaranteed to be less than or equal to every corresponding y value on h of x. Okay. We can tell by this graph kind of demonstrates that. Now, let's say we don't know anything about the middle function except for the fact that it lives between g and h. And let's say we're able to prove that the limit as x approaches a for g of x is equal to L. And then, so the lower function reaches a limit of some number. And then the upper function also reaches the same number. Then what can I conclude about the middle function? The middle function has no choice but to be, in a sense, kind of squeezed between the two functions and also share that same limit. So that's all squeeze theorem is allowing us to say, that if I have this relationship between the lower, middle, and upper function, and if I can somehow prove that the upper and lower function shares the same limit at a point, then there's no choice but for my middle function to also share that same limit. So with squeeze theorem, you're never going to be asked to find the upper one given the lower two, or to find the lower one given the upper two. It's always establish that there's a lower, middle, and upper, and then you're always finding the limits of the outer ones. And if they're in agreement, then I can know what the limit is. If these are not in agreement, then the limit for the middle one is inconclusive, because we need the upper and lower to be exactly the same. Otherwise, we can't make a strong conclusion as to what that limit of for the middle is. So hopefully you guys find that pretty easy to understand, that we're just finding the limit of the upper and lower. And then if they're in agreement, then we know what the middle is. If not, then we don't know.
Okay, let's see which problems I want us to try here. Let's skip number 1 and let's look at number 2 here. Okay, so number 2, it says, let G of H be the function defined by G of X, some polynomial, H of X, some other polynomial. And then they're establishing that there is a relationship between a lower, a middle, and an upper. They don't provide us information about the middle, but we do have the upper and lower established. So what is the limit as x approaches 2 of f of x? So even though we don't have f of x to find the limit, we can find a limit for the upper and lower. So let's find the limit as x approaches 2 for g of x. We can also find the limit as x approaches 2 of h of x. So we just do direct substitution, plug 2 into the g of x function, I get -3. Plug 2 into the h of x function, I get 5. Even though I know my limit is going to be between -3 and 5, we still say this is inconclusive because we're not able to pinpoint the exact limit, at least not with the limited data that we have.
That's some problem.
Yeah, the problem says, what is the limit as x approaches 2? So that means if I can prove that the limit as x approaches 2 of my upper and lower functions are the same y values, then I know that this can also be concluded with the same. So there's only 2 possibilities with squeeze theorem. Either the upper and lower are in agreement, therefore you can conclude what the limit is for the middle one, or they're not in agreement, and then we just say it's inconclusive. But with all squeeze theorem, they have to establish that there is a middle, upper, and lower. If we don't have that established from the beginning of the problem, we don't have the squeeze theorem to use. Let's see. Okay, try number 3. I think this is the most efficient way of applying squeeze theorem is you write out the relationship between your lower, upper, and middle function, and then you just put limits in front of all of them. And then you can evaluate the limits for the upper and lower, and then very easy to see whether my conclusion is going to stand or whether it's going to be. Okay, so this is supposed to feel easy. There's no hidden complexity with squeeze theorem. It's really as straightforward as it seems. Mhm.
Is there ever gonna be like a sort of trick question where they f function satisfies essentially squeeze theorem for an interval, a certain interval, but then they're asking for a limit that's outside that interval.
No. If it's squeeze theorem, it'll be straightforward. I mean, there are some other types of problems and for other theorems that may be a little tricky here and there, but this is not going to be one of them. We're not going to. And then this is a relatively small theorem, so it doesn't. I think chances are, it may show up on AP exam, but it doesn't show up on every one. I think IVT is more established. That one, you're probably going to see it on the AP exam. Squeeze theorem. Oh, yeah. Okay, let's just finish up with 4 and 5. Let's just practice the notations and just get comfortable with it, and then we can move forward. I think we can get ahead. I like to get ahead with from our calendar if possible, because then that just means that we have some extra built-in review days. Right? So I'm not gonna, if we get ahead, I'm never gonna move the test up. I'm just gonna, we're just gonna use that as extra review time. Okay, try 4 and 5.
All right, are we okay? Any questions? All right, page 28. Okay, let's move on to 1.5. Okay, does anybody still need this? Very good. All right. Okay, infinite limits and vertical asymptotes. We're going to focus on vertical asymptotes here. Use the function to answer the following. Identify all vertical asymptotes. So we have a rational function. Let's factor everything. And then we know that vertical asymptote will come from your denominator, right? Basically, any leftover factors in the denominator will be your candidate for vertical asymptote. So let's factor everything here. That's x squared. It's a little bit cut off there. X squared plus 2x minus 8. X squared plus x minus 12. Okay, so where's our vertical asymptote?
Yes.
X equals 3, right? Because x plus 4, this is telling us that there's a what? Hole. Okay, so we're not going to focus on the hole here. We're going to focus on the vertical asymptote. We're going to just go ahead and identify. Now, what do you know about the limit as we approach a vertical asymptote? Limit, does it exist or does not exist? Okay, it does not exist. Okay, good. So we know the limit doesn't exist if we're approaching a vertical asymptote, right? So we've established that. But if we're talking about a one-sided limit, then that's a different story because the one-sided limit is just asking for the behavior, not the full limit. So if it's asking for a one-sided limit, unless the graph doesn't even exist there, or there's nothing for the graph to approach, we're always going to be able to produce some sort of an answer if it's a one-sided limit. Okay. Let me see. Okay, so the graph actually looks something like this. Okay, and we're going to have to do this without a calculator, or evaluate without a calculator. But I just want to kind of show you, just for visual purposes. So let's say the graph was in front of you. Then you would say the limit as x approaches 3 from the left side of 3 would be equal to what? Infinity, right? Because we can obviously tell that the branch is headed closer and closer towards infinity as we follow the left arrow down. Okay. But how do we do this without a calculator? So let's talk about how we can evaluate this algebraically. So let me reduce this function to just be x minus 2 over x minus 3. Let's just take out that x plus 4 there. So let's say we had this problem in front of you. And I asked you to evaluate the one-sided limit. Okay. The first thing we do is we always evaluate the whole number, okay, the integer. So what happens if I plug in the 3? 1 over 0. So this is very helpful because it tells us that there's something going on here, right? If we get a real number, we know that that's our answer, that's our limit. If we get a 0 over 0, we know there's a hole and we can move on with our factoring process. But if we get a 1 over 0, 10 over 0, 8 over 0, we know that visually there must be a vertical asymptote. And we would say the limit doesn't exist. However, if we look at this problem, if we go back to our problem, we realize, oh, it's only asking for a one-sided limit. So we can't just say limit doesn't exist. We have to say either positive infinity or negative infinity. So we have a 50-50 shot, right? We know that it's going to be either one or the other. Okay, so then how do we decide between one or the other without looking at a calculator? And so the most efficient way without a calculator to get to one of these options in terms of how the graph is behaving is we choose a value that is relatively close to 3 from the appropriate side of 3. So maybe you're thinking, well, maybe I can test 1 or I can test 2. We want to be a little bit closer than that. I think the safest number is to use a decimal within the 10th. So what number is a 10th away from 3? 2.9. So I'm just going to test 2.9. Now, I don't care what the decimal value is. I just want to know what the sign is. If I know what the sign is, then that's going to help me decide between one of these options. So 2.9 minus 2, will that give me a positive or negative value? Positive. 2.9 minus 3, I get a negative. Positive or negative is negative, so therefore negative infinity. Okay. Now, here's the danger. The danger is that sometimes a problem can disguise itself as a vertical asymptote without it being one. And just because you see a one-sided limit, it doesn't mean that, oh, there must be a vertical asymptote. I'm going to be testing decimals. Always do direct substitution first. Convince yourself that there's a vertical asymptote before you look at decimals. So I think that's the danger. Sometimes when we see a problem with one-sided limit, our natural tendency may be, okay, I'm going to do decimals to begin with. It may just be a normal limit problem where we're just asking for a one-sided limit. So if the limit exists, then you're going to basically ignore that one-sided limit because the one-sided limit will be in agreement with the true limit, whether it's from the left or from the right. So we always do direct substitution first, convince ourselves that there's a vertical asymptote before we commit to playing with decimals. All right, so let's try limit as x approaches 3 from the right. Again, I'll do the reduced expression. Okay, first things first. Plug in the 3, we get 1 over 0. Limit doesn't exist. We know that there's a vertical asymptote there. Now we look back, realize, oh, it's only asking for a one-sided limit. I can't say it does not exist. I got to decide between either positive or negative infinity. So what's a decimal value that I can choose? 3.1. So 3.1 minus 2 divided by 3.1 minus 3. Again, don't worry about, oh, I got to figure out what that decimal value is. Just convince yourself whether you get a positive or negative, and then from there you can decide what your conclusion is. Just something to be aware of. Let's say we evaluate direct substitution and we get 2 over 0, which means there's vertical asymptote. What decimal value would you choose in this instance? Yeah, negative 2.1. With negatives, everything is opposite, right? So negative 2, negative 3. I want to choose a value slightly to the left of negative 2, so I want to choose negative 2.1. And likewise, if I want to do testing of around an asymptote, and it's negative 2. From the right side, negative 2, we want to choose negative 1.9. Yeah, so just be aware that on the negative side, the plus and minus is the decimals will be different than what you would see on the positive side. Okay, all right, let's go to number 4 and let's practice our steps. So regardless of whether you see a one-sided limit or not, always do direct substitution first. Let that be your anchor starting point. Okay? Because if you start doing other things, it's going to potentially throw you off. So if you always let that be your first step, you're never going to get thrown off because you're going to know exactly where you stand. Are you standing at a real number? Are you looking at a hole or are you looking at a vertical asymptote? We always want to establish that first because with these algebraic problems, you're not going to be able to look at a graph to begin with. All right, so direct substitution gives us which means that the true limit doesn't exist, but we're doing a one-side limit, which means that we know our option is either positive or negative infinity. Now that we know that we're approaching a vertical asymptote and it's a one-side limit, we can do the appropriate decimal test. You would test what? 3.1. Okay. Okay, number 5. First things first, direct substitution. What do we know here? Vertical asymptote, therefore the true limit does not exist. Now, let's say I wanted to ask you a little further and ask you, wait, is there a subcategory for does not exist? Maybe both of the branches are headed in the same direction. If it is, then I can create a subcategory and say that the limit doesn't exist, but positive infinity or negative infinity. So what can I do to see if there's a subcategory? Let's do both sides, right? Okay, let's try that. I'm going to just go ahead and factor that denominator, makes it easier to plug in. So if they're both going in the same direction, if they're both positive infinity or positive infinity, then we can say the limit is positive infinity. If they're both negative infinity, then we can say negative infinity. But if one is positive and the other is negative, then there's no subcategory. We have to leave it as does not exist. So in this case, the one-side limit are both going to negative infinity. We can create a subcategory that the limit doesn't exist, subcategory negative infinity. Okay. Okay, we can pick up tomorrow with 1.5. We'll finish 1.5 tomorrow. Come get your phones. Check your calendar, homework tonight.
We do just
Oh, no. Yeah, so always follow the calendar. I'm never going to change the calendar because we're ahead.
I did.